Many times a statistical study is not about a single proportion, but rather about two proportions, each gained from a separate sample. The idea being to compare them and see if there is a difference between them. So instead of comparing a single sample's results to a claimed value, in this case there is no claimed value, there are simply two samples, and we are looking to see if there is a difference between the proportions gained from each sample. Likewise, we can also do this with means and with variances or standard deviations. For this video, we shall be focusing on the difference between proportions. In this case, the claim is not going to be something of the nature of p is greater than 0.3 or the proportion is equal to 0.6. In this case, the claims are going to be things such as that the sample proportion from the first sample, or the proportion from the first population, is the same as the proportion from the second population. Or perhaps that the value of the proportion for one population is greater than the value of the proportion for the other population. Things of this nature. Now, before we can run off and do this, we have to apply some of the same requirements that we had when we dealt with a hypothesis test for a single proportion. These requirements now must apply to both samples here. So we are dealing with two separate samples, and the rules are that each sample must be randomly selected. Second, that each sample's selection must be independent. And third, that in order to use the normal distribution, we need to ensure that certain conditions are met. The idea here being that the proportion is going to come from a binomial situation. Out of our sample, we will have a number of successes, a number of outcomes that match what we're looking for, and then a number of outcomes that do not match what we're looking for. The very nature of this is a binomial distribution. However, under certain circumstances, a normal distribution may be used as a very good approximation of a binomial distribution. Those requirements are that the sample size times the probability of success has to be greater than or equal to 5, and the sample size times the probability of failure has to be greater than or equal to 5. And this must be true for both samples. So for both samples, we have that the sample size for the first sample times the probability of success for the first sample must be greater than or equal to 5, and n sub 1 times q sub 1, the probability of failure, must also be greater than or equal to 5. But these requirements must also be true for the second sample. The idea is that neither sample can be so far skewed to one side or the other. Basically, as long as the sample size is large enough, we should be fine. In the worst case scenario that p sub 1 and p sub 2 are heavily skewed to one side or the other, a sample size of at least 30 or 40 is usually more than sufficient to make sure that we observe these requirements. Sample sizes of 100 or larger almost always guarantee it. You would need an incredibly heavy skew for that sample size to not be big enough. But as we've seen before in talking about confidence intervals for proportions and testing a claim about a proportion, a single proportion, these requirements must be true, and they usually are. It's very often simply a formality to check them. Now, as long as these requirements are met, that means that the binomial distributions can be approximated by a normal distribution. In this case, rather than have a separate normal distribution for each, we're going to build a single normal distribution based off of the claim that the two proportions are equal. Remember that when we write our hypotheses, the null hypothesis will always include a statement of equality. It's the equality itself that is relevant to the claim, the null hypothesis, because it provides the basis for our distribution. So we establish our sampling distribution it will be normal with a mean that comes from the difference between the two sample populations or sample proportions and a standard deviation of the difference between the sample proportions. Where the mean, the center of this distribution, is going to come from the difference between the population proportions, which, under the assumption that they are the same, this should be equal to 0. Now, sigma is a little bit more convoluted. The standard deviation of our sampling distribution is going to have to come from a combination of the standard deviations of each separate distribution. It's going to come from the square root of P1 times Q1 over N1 plus P2 times Q2 over N2. Either one of these fractions alone provides the standard deviation of the sampling distribution when we're dealing with a single proportion. But now that we're dealing with two proportions, we need to take those two things and add them together before we do the square root. Now, we do run into a minor problem here. We could actually come up with the 0 for the mean based on the assumption that P1 and P2 are the same, and therefore we did not actually need to know the values of P sub 1 and P sub 2. However, in order to get the standard deviation of our sampling distribution, we do need to know a value for P sub 1 and a value for P sub 2. And those values are impossible to know, but they can both be estimated by doing what's called the weighted pooled proportion. So we're going to take one other step here and say that P sub 1 and P sub 2 can both be estimated by P bar. P bar is equal to x sub 1 plus x sub 2 over n sub 1 plus n sub 2. N sub 1 and n sub 2, of course, are the sample sizes of the two samples respectively. X sub 1 is the number of successes in the first sample, and x sub 2 is the number of successes in the second sample. Thus, if we were to look at simply x sub 1 over n sub 1, that would be the value of p sub 1. And x sub 2 over n sub 2 would be the value of p sub 2. Please note that this is not as simple as just p sub 1 plus p sub 2. It's not as simple as that. It is the total number of successes between the two samples over the total number of trials between the two samples. In this way, our value for sigma can be rewritten as p bar times q bar over n sub 1 plus p bar times q bar over n sub 2. And since they both have the same numerator now, that numerator can be factored out. And we have this formula for our sigma. Along with this formula for our mean, but under the assumption of equality, that will always be equal to 0. With these two things in mind, we can now write our test statistic. For any hypothesis test, we need to take the sample data and convert it into the test statistic for our distribution. The test statistic then, in general, is always the sample data minus the mean of the distribution over the standard deviation of the distribution. In this case, then, our test statistic is going to be the difference between our sample means, the difference between our sample proportions minus the mean of the distribution over the standard deviation of the distribution. This is often simplified one step further based on the idea that p sub 1 minus p sub 2 will be equal to 0 under the assumption that p sub 1 is equal to p sub 2. Remember that null hypothesis is assumed to be true, and that provides the basis for the entire test. This is often then simplified to simply be p sub 1 hat minus p sub 2 hat over the square root of p bar times q bar times 1 over n plus 1 plus 1 over n plus 2. And this is our test statistic formula. The rest of this is going to follow the exact same rules as all of the rest of hypothesis testing. So we're going to start with identifying the claim and using it to write our hypotheses, where our hypotheses will always include, for the null hypothesis, a statement of equality between the two population proportions. And H sub A, which is what typically our claim will be, will indicate whether we want a left tail test, a right tail test, or a two tail test. We will need to identify the level of significance. We will be able to use this formula to calculate our test statistic. And then we can either find the p-value from our test statistic, or we can use the value of alpha to find a critical value and make our decision about the null hypothesis from there. Let us look at a couple of examples. First, let's start with an example. In a study of 200 randomly selected adult females and 250 randomly selected adult males who are internet users, 30% of the females and 38% of the males said that they plan to shop online at least once during the next month. We're going to test the claim at the 0.10 significance level that there is a difference between the proportion of female and the proportion of male internet users who plan to shop online. So the claim, let's start with that. The claim is that there is a difference between the two proportions. That means that the claim is telling us that the proportion of female users is different from the proportion of male users. It does not matter which one we put on which side. And to be honest, I did not use P sub 1 and P sub 2 here. I used F and M to distinguish which proportion goes with which. But that is enough then to identify this as H sub A based on its non-equality, which means that our null hypothesis should be that the proportions are equal, which then provides the basis for our test. Now, before we run off, we do need to make sure that we have met all of the conditions here. It does state that both samples were randomly selected. We can assume that they were independent because even with larger sample sizes such as 200 and 250, certainly those are well within the threshold, the 5% threshold, to treat this as independent, even if it is technically dependent. The last thing then is we need to make sure that n times p and n times q are both greater than or equal to 5 for both samples. So for the females, we have the sample size for our females is 200. We have the probability of success for our females is 30%, which therefore means our probability of failure for the females is 70%. Certainly, these numbers are quite large enough to qualify. So if we do n times p, it's 200 times 0.30, and that will give us 60. Therefore, n times q for the females will be 200 times 0.7, which will give us 140. For the males, we have a sample size of 250. We have a probability of success of 0.38, and a probability of failure, therefore, of 0.62. It should be pretty obvious from the size of these numbers that our products will be quite sufficient. We have 95 for n times p, and for n times q, $155. Certainly, all of these are quite well above the threshold of 5. The sample sizes are quite large, and neither one of these samples is so far skewed to one side or the other to overcome such a large sample size. So with all of this said, we are good to go. We fit the requirements for a normal distribution. However, before we run off and do that, we do need to do one more bit here. And that is to find the value of p bar. So before we can run off and start doing our test statistic, we need p bar. P bar is the number of successes from one sample plus the number of successes from the other sample over the sum of the two sample sizes. We actually already calculated the number of successes in each sample when we did n times p. Actually, if you notice, the two values that we calculated for each sample add up to the sample size. N times p, remember, in a binomial distribution, n times p is the mean. It is the expected number of successes. So literally, 30% of the 200 is 60. 60 people, 60 females said that they were going to shop online. So we actually already know the number of successes from the female sample and the number of successes from the male sample. Now, this is not likely to give us a particularly nice value. In fact, it does give us a repeating decimal. And we know from experience that we should try not to use a rounded value if we can avoid it. But if we have to, we could probably round this to 3 or 4 decimal places and get away with it. We now have everything that we need. So we are ready to calculate our test statistic. Our test statistic is going to be the difference between the two sample proportions. Now, it doesn't really matter which one you subtract first and which one you subtract second. This being a two-tail test, it doesn't really matter because the only difference is whether our test statistic is going to come out positive or negative. If we are testing if our alternative hypothesis uses a strictly greater than or strictly less than, then we should always subtract them left to right in the statement. To keep that consistent, I'm going to do that here. Everything that we have done from the very beginning of the wording of the problem all the way through, everything we've done has always mentioned females first and males second. In the hypotheses, it was females on the left being written first and males being second on the right. When we did the n times p's, we did the females first and the males second. When we wrote our p bar, it was the females first and the male second. Everything we have done has kept them in that order. So I'm going to do the same thing here and do the sample proportion for the females minus the sample proportion for the males. Over the square root of our p bar, which is 0.344, etc., times q bar, which is the complement of p bar, 1 minus 0.344, etc. And then that is times 1 over the number of females in our sample plus 1 over the number of males in our sample. Now, in the numerator, we do technically have a second thing being subtracted there, but under the assumption that our proportions are the same, that should be equal to 0. I wrote in some of the values here, but not all of them. Our proportion of success for females was 0.30, and our probability of success for males was 0.38. I don't know why I didn't write those to begin with. Now, this requires a lot of typing, a lot of calculation, so we need to make sure that we do it very carefully. The advantage of a graphing calculator is that it can type in the whole expression all at once, or it can use the ANS feature to not have to round the value of p bar, and that we can just use it directly. So if we're very careful about how we type this in, we should be able to get an accurate value for our test statistic. And our test statistic here should come out to be negative 1.7746, etc., which we can get away with negative 1.77. Again, we can always go back and get more decimal places if we need to, but this is probably sufficient for being able to make our decision clearly. Now, at this point, we can choose either to use the p-value method or the rejection region method. The most commonly used, as we've seen through the last unit, the most commonly used method in the real world of statistics is the p-value method. So we're going to lean towards that a little bit more often here. The idea now is that we are looking at a two-tail test. We know that from H sub A. H sub A was that the proportions were not the same. That is a two-tail test. So we're looking at a normal curve. And our test statistic was negative 1.77. So we need to be looking for the area to the left of this. Our p-value then will come from the probability of having a z-score less than negative 1.77. Now technically, again, we have more decimal places than that, but we can get away with the negative 1.77. That being said, going to the calculator, there's really no reason why we can't use more decimal places, why we can't use the full thing. And if we do, we get a p-value of 0.0379 etc. Now, even if we had used just negative 1.77 itself, we'd still get a very similar p-value using the rounded z-score, which if we're using a z-table, we would have no choice but to do that. We would get 0.0384 after rounding. So close enough that it's not really a big deal. Certainly, this is less than the value of alpha. Remember, we were told to use the 0.10 significance level. Oh, excuse me, I forgot one important thing. This being a two-tail test, this value needs to be multiplied by 2. Which would give us a full p-value of 0.0759, etc. That is the value that needs to be compared to alpha, this being a two-tail test. So our area in the one tail is 0.0379. That is half of our p-value. In any case, though, even doubled, this is still smaller than our value of alpha. This tells us that we should be rejecting, since our p-value, or in this case, 2 times the p-value there, is less than or equal to alpha, we will reject H sub O. Remember that H sub O was the statement that they are equal to each other. And in a two proportion test, that is always what H sub O is telling us. We are rejecting the statement that the two proportions are equal. So what we're saying then is there is enough of a difference between them to say that they actually are different. The formal conclusion statement would say that there is enough evidence to support the claim that the proportion of female and proportion of male internet users is different. Now you might say, well, obviously they were different. The proportion of females was 30% and the proportion of males was 38%. But remember, there's always some natural level of variation. It's possible that we just got a particular group of samples that it just worked out in a certain way, that they came out very close or very far apart. The question is, how far apart is far enough to say that they're actually different? If one came out to be 30% and the other came out to be 32%, well, they are still different, but are they different enough? And that's really what we're looking at here is, we're not just looking to say, are they different? We're saying, are they different enough from our two samples to say, yeah, we're pretty sure that they're different in the broader populations. And that's what our test here showed, that they are different enough. However, I would like to point out that this is not a very large difference between the p-value and alpha. If alpha had been 0.05, we would have made a different decision. So while the proportions were different, they weren't dramatically different from each other. a different value of alpha could have easily changed our decision. Let's look at one more example here. This time, the information is summarized in a table. A medical team conducted a study to test the effect of a cholesterol-reducing medication. The results are summarized in the table. This time we will use a 1% significance level. The question is here, can we conclude, based on the results of our study, that the proportion of patients whose cholesterol was reduced is higher for those that receive the medication than for those that received the placebo? The hope would be that if we're testing a medication that's supposed to reduce cholesterol, we would like to see that it worked. We would like to see, in theory, that giving people the medicine caused more people's cholesterol to reduce than just giving them a placebo. So, let's start with the claim. The claim here, the thing that we would like to look at, is whether the proportion of patients whose cholesterol was reduced is higher when they got the medicine than when they got the placebo. So we're going to call this P sub M for medicine and P sub P for placebo. And what we would like to see is if this is true, that the proportion of people whose cholesterol was reduced who got the medicine is higher than the proportion of people whose cholesterol was reduced who got the placebo. This would definitely then be our H sub A. Again, most cases of this two proportion hypothesis test will be, in most instances, the claim will be our alternative hypothesis. We will be looking at a claim that there is a difference, that one of them is bigger than the other, or simply that they are, as in the previous example, just different, not specifying which one is higher, but simply that they are different. In this case, we are told that we are looking for one being higher than the other. H sub O then should be the complementary statement, but in all honesty, it doesn't matter whether it's less than or equal to, or if it's just equal to. It's the equality of it that's relevant to establishing the test. It's that assumption of equality that matters. So yeah, we could write the complementary statement of less than or equal to, but it's that equality that makes this work, that really drives this. And it's especially important because of how it shows up in the calculation of our test statistic. Now, I'm going to forgo the requirements of checking the requirements in order to use the normal distribution. We can assume that the people here were selected randomly. We can assume that they were independent. And certainly, looking at the numbers of people in each sample, 4,700 and 4,300, we are very, very much well above the threshold of having at least 5 successes, at least 5 failures. We can actually see that in the numbers. This is actually the number of successes for people who got the medication. This is the number of failures for people who got the medication. Both of those are definitely bigger than 5. Likewise, we have the number of successes for people who got the placebo and the number of successes for people who got, or failures for people who got the placebo. And both of those, again, are obviously bigger than 5. So we have clearly met the requirements here. I will hand wave the need to check them so that we can focus on the mechanics of this. What we do need here is we need to identify what is the sample proportion for people who got the medicine and that is 4,399 over 4,700, which of course is going to be quite a nasty number. Definitely not as pretty as we might like, just given the size of these things. This comes out to be 0.9359, etc. We also need the sample proportion for those who got the placebo, which is 3,943 people whose cholesterol was reduced out of 4,300 total who received the placebo. And that gives us 0.9169, etc. One other thing that we need then is P bar. P bar is going to come again from the number of successes for each sample added together over the total number of trials for each sample added together. Fortunately, we actually already have these sums in this table. The sum of the successes is 8,342, and the total sample size, or the total of the two samples, is 9,000. And this gives us 0.9268, etc. So again, some fairly awful numbers here. That being said, we can get away with using rounded values if we need to, and it will still suffice to give us what we need. Again, unless our p-value comes out incredibly close to alpha, or if we're doing the rejection region method, unless our test statistic comes out incredibly close to our critical value, a little bit of rounding isn't going to change our overall decision. That being said, be careful, because in the homework, that rounding may cause your answer to come out off by just a little bit, and it might be enough for the answer to be marked incorrect. So we will use the calculator to try to avoid rounding if possible here. So our test statistic is going to come from the difference in our sample proportions. And again, in general, we should do depending on whether it is a left tail or right tail test. In this case, it is a right tail test, as indicated by the greater than symbol in our alternative hypothesis. If it is a right tail test, then we should expect a test statistic that is on the right or positive. The way that we make that occur is we use the larger of the two proportions first, minus the smaller of the two proportions second. In the denominator, then, we have the square root of our p hat times its complement, which is q hat, times 1 over the sample size of the first sample plus 1 over the sample size of the second sample. And all of that goes under a square root. And this is, admittedly, an awful big thing. But, again, through the nature of the calculator, we can get away without having to round these if we're very careful about how we enter this into the calculator. And if we do it all very, very carefully, we get a z-score of 3.455. We can now take that z-score and find the p-value for it. So again, just to rewrite it here where we can see it, we have a test statistic of positive 3.455, etc. On a normal distribution then, that would put us far out to the right over here. And our p-value, since this is a one-tail test to the right, our p-value would simply be the area in that tail and nothing more. Our p-value is going to be equal to the probability of getting a z-score greater than 3.455. What's the probability of getting something even more extreme than what we actually got? And that comes out to be quite small, 0.0002. That is incredibly small p-value, as evidenced by the fact that we got a very large value for z. We got a very big z-score here. So our p-value is definitely less than our level of significance, which was small to begin with. But that's how small our p-value is. It's even smaller than our value of alpha. And this leads us to the decision that we should reject the null hypothesis. Remember, we are rejecting then the idea that the proportions are the same. We are rejecting the idea that the proportion of people who received the medicine and had their cholesterol reduced is the same as the proportion of people who got the placebo and had their cholesterol reduced. So we would say that there is enough evidence to support the claim that the proportion who received the medication and had their medication their cholesterol reduced is greater than the proportion who received the placebo and had their cholesterol reduced. So as you can see, the general procedure is the same. We have a few differences in that we have to calculate p bar, and that we have a difference in the formula for our test statistic. Aside from that, the entire procedure for the hypothesis testing for two proportions is identical to the procedure for when we have only a single sample.